The hidden secret of forms and patterns. Plato held a metaphysical view that there are abstract mathematical objects whose existence is independent of us in our language, thought, and practices. Just as electrons and planets exist independently of us, so do numbers and sets. And these objects have perfectly objective properties, just like statements about numbers and sets. Therefore, mathematical truths are discovered, not invented. Plato envisioned the existence of abstract, non-physical, but substantial forms, saying that they represent the greatest reality. This viewpoint says that geometric forms and abstract mathematics are entities behind the so-called laws of nature. And clearly, a great number of mathematical equations are true. But many equations we might ponder are not true. A sentence is true only if it succeeds in doing what it purports to do. But why and how are mathematic equations selected? Nevertheless, there really exists abstract mathematical objects that function to control how the universe works. This type of mathematical Platoism has been among the most hotly debated topics in the philosophy of mathematics over the past few decades. Recently, however, it has been proven to be true. And this discovery has astonished the scientific community. The significance of this cannot be overstated, as it means physics must be rewritten and reinterpreted. It is interesting to note here that Werner Heisenberg, the father of quantum mechanics, who formulated the uncertainty principle, drew his inspiration from Greek philosophy. In his book, entitled Physics and Philosophy, he explains how he derived his views on quantum mechanics, which was shaped by Pythagoras. Pythagoras' theorem is used to prove the uncertainty principle, via the Cauchy-Schwarz inequality. Mathematical physics in the modern era. The Unreasonable Effectiveness of Mathematics in the Natural Sciences is the title of an article published in 1960 by the famous physicist Eugene Wigner. In the paper, Wigner observed that the mathematical structure of a physical theory often points the way to further advances in that theory and even to empirical predictions. Paul Dirac's prediction of antimatter from his equation is, perhaps, the most well-known example of this. Dirac derived a waveform equation that is consistent with both quantum mechanics and special relativity. Both quantum mechanics and special relativity share the seemingly magical number, 137. This number is the speed of light in relativity in Hartree units. It's also the inverse of the fine structure constant in quantum mechanics. Another often cited example is Maxwell's equations. Maxwell derived the model combining elementary electrical and magnetic phenomena known since the mid-19th century. As it turned out, these equations also describe radio waves, discovered by David Edward Hughes in 1879, around the time of Maxwell's death. Wigner states, "The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift, which we neither understand, nor deserve." He also said, "It is difficult to avoid the impression that a miracle confronts us here, quite comparable in its striking nature to the miracle that the human mind can string 1,000 arguments together without getting itself into contradictions, or the miracles of laws of nature and of the human mind's capacity to divine them." This viewpoint can be called the philosophy of mathematics. It suggests a very deep connection between mathematics and science. Physicist Max Tegmark has gone further, saying that physics is so successfully described by mathematics because the physical world is completely mathematical. Physics is mathematical, not because we know so much about the physical world, but because we know so little. It is only its mathematical properties that we can discover, says Bertrand Russell. And, Carl Friedrich Gauss said, God arithmetizes. The most incomprehensible thing about the universe is that it is comprehensible, says Albert Einstein. Einstein also formulated the EPR paradox to challenge the idea of spooky action at a distance. John Stuart Bell, in making one of the great discoveries of physics, developed a theorem that states, no physical theory of local hidden variables can ever reproduce all of the predictions of quantum mechanics. The existence of locality implies that there is no spooky action at a distance, no faster-than-light action. Bell proved this wrong by establishing quantum entanglement at a distance. Therefore, reality is non-local. Arguments against this include 1. Absolute or superdeterminism, no free will, and 2. The particles involved and the universe simply already know what the measurement and outcome will be, indicating pre-knowledge. Such arguments are not popular. Let's go back to the beginning. The belief that God created the universe according to a geometric plan has ancient origins. According to Plutarch, Plato said God geometrizes continually. Pythagoras, succinctly, summed up his vision saying, all things are in numbers, the world is living arithmetic in its development, a realized geometry in its repose. Pythagoras saw in these signs and designs, everywhere present, the thought forms of the eternal mind, else they would not be the natural, self-sought forms of matter. Sacred geometry refers to the unnatural effectiveness of abstract mathematics to control the laws of nature, and the inexplicable role of geometry running the universe. Sacred geometry involves sacred universal patterns used in the design of everything in our reality, most often seen in sacred architecture and sacred art. The basic belief is that geometry and mathematical ratios, harmonics, and proportion are also found in music, light, and cosmology. Next comes the clincher, the Amplituhedron at the heart of physics and its implications. This hidden gem takes a geometric form. It is called the Amplituhedron by its discoverers in 2013, Nima Arkani-Hamed and Jaroslav Trnka. This hidden form enables simplified calculation of particle interactions in some quantum field theories, such as planar, supersymmetric Yang-Mills theory, which is equivalent to perturbative topological B-model string theory in twistor space. An amplituhedron is defined as a mathematical space known as the positive Grassmannian. But practically speaking, it challenges the very notion of time and space. It defines space as an emergent quality. Potential force energy becomes emergent space. It further suggests that reality is non-local. Even more astonishing, unitarity, where probabilities go from 0% to 100%, emerges from this hidden geometric object. In essence, this geometric object defines the scattering pattern of particles in a certain volume. Calculations can be done without assuming the quantum mechanical properties of locality and unitarity. In amplituhedron theory, locality and unitarity arise as a direct consequence of positivity. They are encoded in the positive geometry of the amplituhedron, via the singularity structure of the integrand for scattering amplitudes. Though this is a toy model describing particle interactions, it nevertheless does work. In fact, quantum mechanical calculations can be done on a single sheet of paper that used to require hundreds of pages of Feynman diagrams and reliance on supercomputers. Emergent space indicates there is an unknown pre-emergent, unmanifested, primordial energy concealed in the universe. But through some unknown process, pre-space or potential space or primordial energy is actualized in some way, evolving into, and associated with materialization, which is gravity responsive. That is, emergent space implies that our universe gradually evolves over time, becoming more settled and predictable. This statement, though true, contradicts the second law of thermodynamics. If the second law of thermodynamics were true, the evolutionary origin and process would deteriorate, leading to universal chaos. However, it now appears that the universe evolves from chaos to order, in opposition to well-accepted thoughts on physics. And, if this is true, there has to be an over-controlling, non-physical force energy behind this process. Supersymmetry is a concept that physicists believe is necessary to extend what is called the standard model of particle physics. However, this concept necessarily implies that particles are massless. It has long been believed that the Higgs boson must exist in order to give mass to particles. Recently discovered, the Higgs field is tachyonic, which means symmetry is broken through condensation of particles. When this happens, a particle absorbs components of the Higgs boson, acquiring mass and making it respond to gravity. Haiyan Jung of Cornell University, in a 2015 paper titled Emergent Spacetime, Reality or Illusion. Paraphrasing, Jung said, "There's growing evidence of emergence systems including gravity and spacetime. We observe that non-commutative spacetime necessarily implies emergent spacetime. Emergent spacetime may rescue us from the doomsday of metastable multiverse as quantum mechanics did from the catastrophic collapse of classical atoms. Emergent space implies that our universe, the one we live in, is a derived universe. That is, the creation, control, and maintenance of our universe implies the necessary existence of a core, original, or feeder universe and bridge between universes according to the Einstein-Gödel-Rosen solution of Einstein's equations." Background independence in physics. Background independence is a condition in physics that says equations of a theory need to be independent of the actual shape of spacetime. Fields cannot be defined arbitrarily within spacetime. Further, the theory must be coordinate-free, which means it should not refer to a specific coordinate system. The leading theory in this regard is called loop quantum gravity, which is formulated by quantization of relativity. This theory presents us with a specific cosmological portrait of the universe, where space is emergent, and time might be emergent as well. It also suggests the universe is cyclical and dynamically driven by geometric structures, and thus, follows more closely the Einstein-Gödel-Rosen solutions than does string theory. In string theory, we encounter the landscape problem. The theory allows thousands of false vacua. It doesn't single out a specific landscape, and thus, is not background independent.